well, but I've been informed that some of them may not work, so I will just distribute those, and then in a process, maybe we will have some more, but I am not sure. So if you have laptops and you want to follow basically with me, you can. So
is it possible to download it from anywhere?
it's like 2.3 gigabytes.
Oh.
Yes, it is possible, but it will take a while.
Okay, thank you.
On each flash drive, you have 3 files. Basically, so you have a VM image with all the necessary tools. The second file is a BIOS binary, and then a third file is a startup script. Basically, all you have to do is just start the script. It will start QEMU KVM virtual machine with the disk image provided and BIOS image, which is also on the flash drive.
So can I introduce?
Go ahead.
So hi guys, let me introduce you to this workshop which will be done by Michal Sekletar, and it will be about introduction to UEFI application development. Please ask questions. Michal can give you these scarves if you are active enough, so please do. Also, evaluate the session. You can let us know about your opinion on Twitter or post a blog. Also, I would like to remind you that tomorrow is great contest and in the end of the DevConf, and you can get some awesome prizes like Raspberry Pi, UB keys, which are for the keys. And that's also. Please enjoy.
Thank you for the introduction. So yeah.
I have a question. Would it be safe to do it on real hardware instead of virtual machine?
That I will get to that. Okay, so let me start with the first slide, which is basically your question. Yes, I mean it depends. It depends on your firmware and your platform. I will take no responsibility for any bricked machines during this workshop, so that's why we have VM image, and we will be doing the work in a virtual environment, because yeah, I mean it's every time you interact with the firmware, it may work. I mean it should work, but in a real life there are some vendors which screw up, and then you will brick your machine. So first, every time you do something like that, like I don't know, writing to EFI variables or updating the firmware, check first on forums, on OEM or manufacturer website whether it is safe, because I can't tell. It depends on the platform. So yeah, we will be using the VM image because it is safer to do it this way. So like I said, on that flash drive you have 3 files. So it's basically a disk image, BIOS binary, and startup script. Script is that simple. It's only just shortcut to call QEMU. So yeah, let me first tell you what will be the contents of this workshop. So the title is Introduction to UEFI Development, which is sort of a bit misleading, because it is not only about the development, because I don't think it makes sense to do some live coding in this workshop. I think that and it doesn't make sense to do that as well, because I have no idea who actually has some prior experience with UEFI and C language, and has basically some prior experience with programming. So there will be something like development work at the end of the workshop, but before that I will start with some other things. So first I will show you some SecureBoot demo. Then I will talk briefly about legacy BIOS. I will clarify vocabulary a bit I will be using in this workshop, because there is a lot of terms floating around. Everybody is using similar terms to address different things. So I will clarify what I mean by what, basically. Then I will talk briefly about UEFI. Then I will talk about SecureBoot more and actually show you step by step how you can basically take over your own machine, because so how you can take over your own machine and how you can use SecureBoot for your own benefit. And then we will get to the Uefi development, which will where I will address like how to set up a basic environment. What do you need to actually write Hello World application which can run directly on top of the firmware? What build tools, what other tools are necessary, because it is a bit different than basically the GCC normal workflow.
This image is important just for development?
That image contains SecureBoot stuff as well as you can use it for SecureBoot setup and demo, and UEFI development tools are also installed. And inside that image, in a root home directory, root user home directory, is actually very small UEFI applications, basically Hello World example. And there is a script which will set up SecureBoot on that VM. So that image should address like both things, SecureBoot as well as UEFI development. So I will start with the demo, because I think it is, at least I think it is interesting to see first where we want to get to. And so let me ask, who knows what is SecureBoot? A couple of people. And who thinks it's a bad thing, or who so I will use basically the same script as you have. So I started the VM. You can see it. So this is the bootloader environment. That is actually systemd boot bootloader. So I have Fedora rawhide in that image. So let me start rawhide. Hopefully it will start, and it should be quick because it's systemd inside. Yeah, it's quick. By the way, password for a root user is Red Hat, and there is also a test user, and the password is the same, so Red Hat. So like I said, in a directory of the root user, you can see Hello World example. Then there is a SecureBoot demo and some Fedora CA certs. You don't have to be bothered with those. I left them because I would like to be able to boot kernel signed by Fedora signing keys. So, and if you accidentally delete Fedora key, it's not that easy to recover that key, because, well, it's just not that easy. So SecureBoot demo. Now let me show you that currently. So for systemd bootloader, we have a command line tool called bootctl. It has a couple of top level verbs basically, like status, install, update, and remove. If you don't provide any parameters, it will do status. So it is going to tell you which version of UEFI firmware you have, what is the current secure boot mode, and a couple of other important informations. So as you can see, my loader is systemd boot, and yeah, and SecureBoot is actually now disabled and platform is in setup mode. What those things mean, I will get to that. So I will just run. Okay. So yeah, it requires test setup script requires one parameter. It is just it will be used as a part of a distinguished name for generation of certificates. So it generated some certificates, and printed some debug output, and it enrolled keys into the firmware. As you can see, I have a couple of keys enrolled, and I have Fedora SecureBoot CA key enrolled as well. So I don't have to resign my kernel and all kernel modules.
These are stored in EFI?
Yes.
Yeah, okay.
They are actually enrolled in an EFI firmware. So now I should have systemd boot x64 EFI, and that is actually, you'll see, here is the unsigned version, and here is the signed version of the bootloader. So I signed bootloader with the key I just generated, basically. And now I can copy the bootloader to the final destination, which is boot EFI systemd. So I will overwrite what's currently there. Okay, that should be it. Now if I reboot the machine, okay, so first thing, I was able to launch a bootloader. That's a good thing, because now SecureBoot should be enabled and enforced. So that means that my bootloader is correctly signed with the correct keys. So I can now launch Fedora, Rawhide, and it seems like, okay, so it started up. So that means also that Fedora keys is properly enrolled in a EFI firmware, because I didn't do anything like resigning of the kernel, so Fedora keys is in there. That's why I was able to boot that kernel. And now if I run bootctl, I can see that SecureBoot is enabled, and I am actually in a user mode. I will cover SecureBoot modes during the presentation. So now I can look in a system keyring, and I should see that yeah. So I have my own keys and Fedora key in a system keyring. So no Microsoft key, no Lenovo key, no other keys than this. So no one else is basically able to load any malware into my kernel. Basically, also no bootkit malware should be able to succeed on such a setup, because unless somebody stole my keys, right, and assigns malware with my keys. Okay, so that.
Or unless somebody hacked your utility and it lies to you.
Yeah, I mean,
what KQTL prints is true.
Come again? I didn't get that.
Well, bootktl said to you that the secure boot is enabled and the setup mode is user. How do you know that this is true, not the fiction created by this binary?
Well, it reads.
You know it by looking at this
It reads.
letters on the screen?
I mean,
it does this, not invents this.
Well, it depends. You have to trust your firmware, right? because it's firmware is telling that basically via the EFI variable, which is exported to the kernel, and kernel exports that to the user space as a special file system. So if you don't trust your machine vendor, I guess you are screwed anyway, right? Whatever you do.
Yeah, I mean, all this trouble just to still have to trust something.
Yes, of course. You have to trust your firmware vendor and your hardware vendor. If you don't trust Intel and
There are easier ways to own the hardware.
Hmm?
There are easier ways to own hardware. Just use the Efi option.
what?
There's easier ways to own the hardware than using this. If you really wanted to, you don't trust Intel, you're screwed.
If you don't trust Intel, then running anything on the processor is a moot point.
Yes, of course, because I mean I don't know what is running in system management mode. I can't tell, and system management mode can run basically any code, and even operating system doesn't know what is running. So if NSA has backdoor in Intel hardware and some code is running in a system management mode.
The problem may be in software, which you already have. You think that it's only trusting these keys and it shows you these keys, but you don't actually know it by when you type the letters.
Of course.
You didn't check all the megabytes of code between you and hardware. No.
No.
So we go through years and I don't know how many years of development for what? For just additional pain in the ass?
I don't necessarily agree because
Yes, you've hit a basic point. You have to trust your hardware vendor at some point. So we can't really fix that here.
Yeah, it's probably not part of this.
I mean the SecureBoot is a protocol for building a chain of trust, and that chain of trust has a trust anchor. And if you don't trust your trust anchor, then I mean write on your own firmware and do your own hardware. I don't know. I mean you have to trust somebody at the end. So yeah, question?
Well, even if you fabricate your own hardware, there's so many people involved in the process that someone might just actually modify your hardware design anyway and put something in your hardware, and then you are essentially doomed.
Yes, of course, because you would have to also verify the compiler for VHDL or Verilog or something you are using to design the hardware.
Not software.
Take a buffer and actually take a microscope and inspect each die on the buffer to see if it's.
Yeah, of course. So, but at least if you accept the premise that firmware is not lying to you and your firmware vendor doesn't put backdoors in the firmware on purpose, then you can be sure that, for example, now even somebody hacks my machine and will run some malware under the root. It can't install kernel modules without my permission, basically. Now I have signing keys on that machine, so I would have to, of course, took signing keys to some other place, safe place, not to leave it on the machine. That's of course just the demo setup we have here. But in a real life, you would have to secure your signing keys, and then.
Well, you have several hundreds of kernel modules already. You never reviewed their source.
Of course.
And what they do, and maybe one of them already has something. And they are all signed, so insert a module for your, I don't know, USB keyboard, and there is something you didn't know.
Yes, of course, but
You trust open source?
I mean, if you don't trust anyone, then you can't use any software today unless you write it, and even then you don't have any means to run it because you don't trust the platform where you run it. So
yeah, that's what I'm saying. You already trust your kernel, your modules. So why all of this? Why this signing nonsense? I don't have SecureBoot here. I don't expect here to magically new modules to appear with viruses. That's the trust I have.
and I don't think that's
Why
necessarily.
do you need these keys to have some additional?
I don't think that's necessarily a good thing to trust that you will be so lucky that you will never encounter any rootkit malware. I mean, you can trust that it will never happen to you, but you can take measures to make sure that it never happens to you. So that's the thing, that's the point, right? Or I don't know. Anyway, okay, so that was the demo. Let's go back to the slides. So yeah, I will try and summarize some facts about the BIOS and also clarify what I mean when I say BIOS, firmware, UEFI, EFI, and whatnot. So basically, by legacy BIOS, I will be addressing a type of the firmware which was pioneered basically by IBM, and it was standard in all IBM PCs since like early 80s basically. So yeah, and actually the interesting fact I discovered when I was doing the research for this workshop that IBM PC wasn't the first computer which used like BIOS-like firmware. There is this sort of exotic and very old operating system, CP/M, which was running on a computer which actually had something like IBM BIOS firmware even before that. So maybe IBM took some inspiration from that. I don't know. I just mentioned it on the slides as interesting fact. So yeah, so IBM pioneered this concept of BIOS as we know it. Then a couple other vendors implement basically the same thing. They reverse engineered what IBM was shipping on their computers and implemented similar set of features, similar set of interfaces. BIOS is quite old actually. It is here from late 70s to 80s and up to late 90s basically. And even today you can see computers which use like legacy BIOS, non-UEFI based BIOSes. Problem with the BIOS is that it is written in assembly, and if you want to extend it, you can buy some license from some vendor like Avard BIOS, EMI BIOS, couple other vendors are around. So you can buy license. They will probably give you the source code like in assembly, and you have to extend it also in assembly. The execution environment is not that great. I mean, it's running in 16-bit real mode, and you can address like 1 megabyte of memory, and that's it pretty much. I mean, there are different implementations, different vendors these days, so it's hard to generalize. But well, that's probably the limitations which apply to almost all of them, basically. So, what actually BIOS does? So, you reset your machine, then after the reset, CPU will start executing some code defined by reset vector. That will probably do some basic CPU initialization, and then it will run something called post, power on self-test. Basically, it will initialize chipset, main memory, video adapters, other hardware you have like PCI subsystem, USB these days, and whatnot. Then it will continue with boot device selection, and then if you are lucky and you have something you can boot from, it will actually load the OS loader or operating system. Basically, these days on Linux machine, it will usually load grep or part of the grep, which then will load grep. And usually it includes setup utility, where you can do some basic system configuration and configuring hardware subsystems, stuff like that. Okay, so problems. I already mentioned that execution environment is not that great. Other problems are that BIOS doesn't scale really well. Intel engineers in late 90s, when they were designing Itanium platform, they basically saw that there are issues of running really primitive code basically on a new 64-bit machine, which Itanium is or was, and so the BIOS just doesn't scale well on big iron machines like big servers, which was the plan with the Itanium. Yeah, and it's proprietary. There are multiple vendors, but still, there is no open source implementation I know of, and there are no standard interfaces. So I have no idea how the vendors communicate or what they do, but I don't know. I guess somebody implements something first, and then the other vendor comes along and reverse engineers how is that functionality done and does something similar. So now something about UEFI. So UEFI is also type of the firmware, but it is not legacy BIOS code from the vendors which were displayed on previous slides. It is completely new thing, new implementation of the firmware. So why should you care? Probably runs on your laptop. I don't know who doesn't have in this room laptop with UEFI. I guess almost everybody. Oh, everybody has. It's extensible and it is standardized. So actually, you're on your own. You can develop extensions to that firmware, and it's written in C. And another good thing is that now we can see that some cooperation between OEMs and industry vendors is formed. Basically, they still compete with each other, but at least they can sit around in one room and decide what they want in their basic platform. So you take two completely different computers and you can be sure pretty much that at least what is in the UEFI spec will work on both of them, and it doesn't really matter who is the manufacturer. So yeah, bit of a history about EFI and UEFI. So UEFI stands for Unified Extensible Firmware Interface, and its predecessor was EFI. That is the thing which Intel people wanted for their Itanium platform. So in late 90s, they developed EFI, which eventually evolved into UEFI. That is the name of the specification as well as industry standardization body behind the specification. So it is formed by big companies, by big vendors, and it has different work groups, which then have some subgroups, and each group is responsible for part of the specification. And from time to time, they get together, and release a new version of the spec. And the newest version is 2.6 from January of this year. So UEFI-based firmware goes through the different steps while basically booting your machine. So I will very briefly cover what those steps are. Maybe some of you already seen this picture because it's used so many times, but it has been used so many times, but I think it really captures what are the main phases of the system boot in a firmware which is based on UEFI. So we will start here with the first phase, which is called sec or security phase. This is the so basically once the machine is powered on, it will jump into some code which basically verifies ROM where the firmware itself is stored. It verifies the integrity of the ROM. Then we transition to PEI phase, which is pre-EFI initialization phase, and in that phase we are still running from ROM out of flash execution. We don't have any main memory, so we use so that code which is running is part assembly and some part already in C. It has to use CPU caches as ROM on Intel platforms. I'm not sure what ARM-based platforms do. Maybe.
Well, it can be done both ways. You can lock either caches on ARM,
Mm-hmm.
so essentially you lock the D cache and then you use that for stack. On Intel you always use locked CPU caches. On MIPS and ARM you can also use SRAM if you have that option in the CPU. It's not necessarily there, it's optional.
Mm-hmm.
If it's not there, then use the caches. On PowerPC, you, I believe, lock caches as well.
Okay, so basically every platform uses what is available, and that will
Locking
be.
caches is harder than using the on-chip SRAM.
Hmm?
So if locking caches is actually harder than the on-chip SRAM,
Mhm.
so if you have on-chip SRAM, you use that.
Yeah.
Because it's readily available there.
Okay, thanks.
Yeah.
So, but the main point of this phase is basically initialize memory. Programming without memory is hard, and that's why we want to have like main memory available for the rest of the system boot. Then we transition to driver execution environment, like it's Dixie phase, and in that phase, bulk of the firmware code is basically running. The biggest portion of the firmware code is running in this phase, and in this phase we execute Dixie drivers, which implement architectural protocols which are defined by UEFI platform initialization specification, and then we dispatch all EFI drivers, and those drivers provide us with EFI or they implement EFI protocols, which we can then use in applications. So and then we transition to boot device selection phase, and then we usually we either start up some operating system loader, or we can load basically operating system itself, because Linux these days carries like EFI stub loader in a kernel. So kernel binary can basically masquerade or trick firmware into thinking that it is itself EFI binary. So firmware can directly launch Linux if we don't want any bootloader or OS loader. And EFI specification basically only covers this blue strip UEFI interface. So that is the main interface to the firmware. Okay, so I basically covered all this. So now we have basic understanding what UEFI is, how it roughly works. I mean, to describe it in detail, it's too much work, and the specification, like the specification of the interface has almost 3,000 pages, and there are a couple other specs, so it is thousands and thousands of pages. So I will be not covering anything else, because I don't think it makes actually sense to do it here. So, are there any questions about this part or comments? Please feel free. Go ahead.
Is there a way how to boot 16 bits code from 32 bits UEFI?
That's a good question. I have no idea. Maybe somebody else can answer that. I actually never tried that, so I don't know. I can't tell. Does somebody know if it is possible to boot 16-bit code? I would be surprised, but
Well, I mean, if you have UEFI, you have such a performant machine that you can run it in QM, right?
yeah.
If you really need that.
So, why did you ask? Just out of curiosity, or you have use case for this?
Use such maybe third-party software, I don't know, Attendees or something similar.
Mm-hmm. Sorry, I don't know. I don't know.
And another question.
Yeah, go ahead.
Where the SP standard stands in the UEFI standard? Is it subset or?
What,
something
please?
different? SP.
Oh, ACPI. ACPI is like. I'll just. So, uefi.org specifications. So here are all the specifications which are produced by UEFI forum, and ACPI specification is separate from UEFI specification. So, but it is very, very related, or I mean, it is produced by same group of people, basically.
Is there something like ACPI tables in the UEFI standard, or it's different, or coexist together? Or?
I would say those two standards like coexist together, but I don't know if that answers your question. We can boot services time. I mean, I haven't really studied what's in the spec in the newest version. I actually found out that 2.6 was released like a month ago, so but it doesn't seem they changed that much. It seems that it is basically the same thing as it was before. Yeah, but to answer your question, ACPI is separate standard, so it is not described in this document, but it is separate. You can.
I'm asking because when I boot my laptop in the UEFI mode, I can see the ACPI tables there. So it's vendor extension, or whether it is mandatory by the UEFI standard.
I honestly don't know. No idea whether that's mandatory or vendor extension. I can look for ACPI. There is a couple of matches. Calls, position. Okay. Yeah. So seems like that ACPI tables are there is a protocol defined by standard. Install ACPI table, uninstall are the methods of the or parameters. Yeah. So this is.
Okay, and is it mandatory or is it extension?
That will be mandatory, I think.
Okay, thank you.
Yeah. Okay, so now I will cover one specific protocol, which is SecureBoot. I picked SecureBoot because I think that there is a lot of misinformation about SecureBoot in a Linux community, and Linux users are sort of, I don't know, sensitive to that subject, so I picked it on purpose, sort of, so we can discuss SecureBoot issues here. So basically what SecureBoot is a protocol described by chapter 30 of UEFI spec, and basically it is a protocol for building a trust relationship between the components which are involved in a boot process. So it builds trust relationship from the firmware up to the operating system, and each component in that trust in that chain of trust basically verifies the next component in the chain. So that's in a nutshell the main idea and main concept. So to talk about SecureBoot, we need to first understand that there is crypto involved, and there are a couple of key databases. So, and those keys in those databases are used to build that trust relationship, basically, or they provide you with the way where you can verify the trust. So there are four main databases described by UEFI SecureBoot. First one is PK, platform key. It is database which contains always only one key. Then you have KEK, key exchange key, also database which contains only one key. Then you have DB, which is signature database that may contain more keys or hashes. And then database, the last one is DBX, and that contains basically keys which are revoked. So it's a revoked database of revoked keys or hashes, known hashes of a malware. So if the new malware, which for example, I don't know, like there is some attack against Microsoft Bootloader, Windows Bootloader, they can release a new version, a patched version, and they can enroll a hash of the old one in that database, and that means that platform firmware will never boot that or will never run that code anymore. So that's the point of the DBX database. And in those databases these days, the spec says that there are multiple options what can be stored there, but basically almost every vendor these days and every firmware implementations I encountered supports X509 certificates with RSA keys or SHA-256 hashes. So this is the diagram which shows you which secure boot mode actually exists. In the demo you saw that I started here in the setup mode, and in setup mode I can basically run whatever I want. Secure boot is effectively disabled, and then I enrolled keys and I transitioned into user mode. So in that mode, SecureBoot is enabled and enforced. So we will check signatures and we will build the trust relationship, and we will actually refuse to boot unsigned code. And there are two other modes. I will not bother describing for what is audit mode, but deployed mode could be. It can be said that it is the most secure mode. So you can transition from the user mode to the deployed mode, and in that mode Basically, the EFI variables are read-only. You can't change them unless you can't change them programmatically. You have to be present at the machine and transition back to the user mode, or transition back to the user mode, and then you can programmatically change the keys. Or you can also, there is a platform-specific way how you can see here, a platform-specific way how to transition from user mode to the setup mode. Question?
Where is the mode stored? Like, if I change the mode to deployed, what physically changes? Is there like an EEPROM somewhere that's got that data in?
NVRAM. So it is exported then as EFI variable, basically.
Which is stored in the NVRAM. So what happens if you just clear the NVRAM?
I mean, the spec doesn't says where is it stored. It says that what are the requirements for storage. So I think at the end of the day, the fact where is it stored on the given machine would be platform specific, but it has to comply with the requirements which are given by the spec. So, for example, that database must be tamper-proof and stuff like that. And
You can just remove the backup battery and
I think it should survive that.
Well, if it's NVRAM, it's non-volatile.
Yes.
well, we can raise it like
Yeah.
the chiplet thing.
So you are not supposed to be able to do that, but well, that document is just a spec. So what actually gets to the end users, I mean, it's hard to tell. It would be nice if all the vendors complied with the specification, but yeah. Oh, question?
What I believe these secure bits are stored in the TPM chip, which is now no longer TPM because it's part of chipset.
Yeah.
And this is protection so that when someone actually has physical access to the machine, they can just pull out the TPM chip, put something else in there, and subvert the security. At this point, you would have to actually decap the chipset and start digging into it with a microscope, and then you can subvert the security. That's why this sort of variables should be stored in your chipset somewhere there.
Like I said, the spec itself doesn't says where it should be stored. It puts some requirement on that storage.
I believe you should check the management engine documentation. It should be there.
Mm-hmm. Yeah, maybe. That's maybe the case. I don't know, but I don't recall that the spec itself says that. So maybe some other document has more information on that. For
There's
like.
a lot of that stuff from Intel, right?
Hmm?
There's a lot of documentation from Intel on all this stuff. So.
Yeah. Okay, so those are the modes, and now as for the benefits from my point of view, that's sort of open for discussion if you may agree or not. But so like I said, chain of trust from the firmware to the OS should protect you from the bootkits. No unsigned code running in kernel, and only signed drivers are loaded, so more or less no rootkits, basically. So there are risks involved as well. So on most machines, that chain of trust include third parties. So it's not only you and manufacturer of your machine, but typically Microsoft, because your laptop probably has Windows 8 sticker on it, or maybe Windows 10 these days. And Microsoft mandates that if manufacturer wants to put Windows sticker on their laptop, Microsoft has to have their keys in a firmware by default, and SecureBoot must be enabled.
Can I ideally use keys?
Yes, of course, you can. So SecureBoot actually, and that is another thing which is not mandated by the specification, but this is mandated by Microsoft. can't be disabled on the ARM-based devices with Windows 8 and newer. So, yeah, on Intel-based hardware, we are fine. We can still run whatever we want. Basically, we throw away keys which are provided by the vendor. We install our own keys, Red Hat key, Fedora key, and we can run whatever we want. But on ARM, we are sort of out of luck because there's no way how to turn off SecureBoot. So if you buy, I don't know, tablet with Windows 10, then you can't disable or shouldn't be able to disable SecureBoot. I can't really imagine that Microsoft would allow such devices to be sold to the end customers if the manufacturer doesn't comply. But I don't know. I wasn't very actively looking for cases where this is actually not the case. So yeah, SecureBoot doesn't prevent infection of your machine from malware. This is not what it does. You can still have your machine hacked even if you have SecureBoot enabled. It's just that the hacker will probably be not able to inject any code to the kernel. I mean, via the measures of loading kernel modules. He can, of course, trigger some bug in kernel via other means and possibly inject code this way.
Do you sign the NRD as well?
No.
So that's not going all the way to user space then, is it?
No, it is going up to the level of the operating system and not to the applications.
So if the kernel's booted, that's the line.
That's the line, yes. So if you have your initramfs or if your initramfs was tampered with, you are again out of luck, and SecureBoot will not save you, because the problem with initramfs is that it is generated at install time. When you are installing Fedora as the last step of installation, there are post scriptlets, post-trans scriptlets running, and then as part of the post-installation process, initramfs is generated, so it can't be signed by Fedora or Red Hat. So initramfs is not signed these days. There is some work going on to address that. Harald Hoyer is working on pre-generating of initramfs and storing hashes of initramfs and kernel command line hashes to TPM. So system then can do remote attestation and prove to the other party that it really booted with the kernel command line parameters it was supposed to boot with. Because of course you don't even have to really change initRD. If you are present at the machine, you can just say init equals bin sh, and you don't have to do anything else to take over the machine, basically. So once we have possibility to do remote attestation secured by TPM, then we will be able to tell that, okay, if I have this setup in my environment, in my organization, those machines can't be subverted this way, because hashes of the kernel command line will be stored in TPM, and then it will do remote attestation to a server. So also there are problems if you are running with SecureBoot enabled. Currently on Fedora, I don't know about policies in other distros, what they do, but in Fedora, direct I/O to dev-kmem is disabled. Then writing to a machine-specific registered via MSR kernel module, is not supported. Also, if you want to so kexec is also disabled, and that implies kdump is also disabled. So yeah, I mean, in enterprise environment, it's not that great because kdump tool is used a lot, and kdump uses kexec functionality. There is so if your basically if your kernel crashes, there is a separate kernel which will be kexec, and it can then collect some more information about the crash, and those information then can help support engineers. Yes?
Isn't there a new kernel function for like half a year where the old kernel directly loads a new kernel and so can do that in a SecureBoot compliant way?
Yes, that may be the case. I saw patches on kernel mailing list, but
They got merged like half a year ago, I think.
Ah, okay then.
Maybe it's not used yet in Fedora.
no, I don't think it's used in. So basically, I'm here describing Fedora setup, but it is good to know that patches upstream has been merged. So yeah, so kdump will be usable then. So and that's good. Thanks.
And what about third-party kernel modules like VMware tools or drivers? After you update the kernel, you will regenerate it. Who will sign it?
Well,
Or I just reboot and I will have no network.
So yeah, I mean, with the security features and security, it's always a trade-off, right? So there is some more work involved. So basically, if you have third-party modules which are already signed, me on my own laptop, I don't have any hardware which requires those, so I didn't dealt with this problem myself, like personally. So, but I would think it is possible to strip the signature from whoever is delivering the module. I mean, NVIDIA, VMware, whoever, and then re-sign it with your own key, and then you can load it. I mean, it's a hack, but it can be done, and yeah. So I think that there is no other way. If somebody knows about some other way how to do that more effectively, please speak up, because I don't.
So can you sign the module with one key at a time?
I think so. And also in Fedora, hibernation is disabled, but again, I personally don't use that, so it doesn't bother me.
Does suspend work?
That's the suspend, basically. Hibernation and suspend. I mean, suspend to RAM.
Yeah.
That works. So that is suspend to disk. Sorry. So now, as for the demo. Okay, so in demo I showed you at the beginning. Basically, those are the steps I did, or I have a script which did those steps. So basically, if you want, you can check in a SecureBoot demo folder. So this is the script, and these are basically the steps it does. So first thing, it checks some parameters that's not interesting. Then it will generate some random UUID unless it is already provided in a file like owner GUID. Then we basically, using OpenSSL, generate RSH keys and X509 certificates. Then we convert those certificates to the form which can be then used by or can be enrolled into the firmware. It's called EFI signature list. So it is, you can imagine that it is like the certificate is very concrete thing, and standard says that you can enroll a couple other things except the certificates in a firmware. So on top of the certificate you have that EFI signature list, which basically encapsulates the certificate in our case, but it can encapsulate a couple other things like standard hashes. Again, a specification is very concrete. What can be stored in a EFI signature list, and then basically what we do, we sign the signature list, and the signing is done here. It is a bit of a hack, but in a real life it would work that you have you generate your own platform key, and once you enroll that, you are the platform owner, basically. That is the sort of the meaning of that key. Whoever has that key enrolled is platform owner. So in a default setup, OEM basically owns your machine because the key belongs to the OEM. So if you change that key, then you become the platform owner, and then all the other keys in key databases I showed you before, like KEG, DB, and DBX, can be changed by you. And the way you do that is you have to generate it's called authenticated updates to those key databases, and the key databases. Keys in those databases can be updated always by the updates, which has been signed by the key from the database, which is above the database. So as was it on a slide, first we had PK, then we had KEG, then we had DB. So this is the hierarchy. You have your own PK, you own the platform, then you can generate authenticated update to KEG database, and you can basically append to you can basically change the key in a KEG database. So or add the key to the KEG database, and you sign with the platform key. And then if you want to change key in a DB database, that would be the key you are using for signing, for example, your own kernels or your own EFI applications. You will sign that update to the DB database with the key in KEG database. So that's the hierarchy.
So what happens with your own key in the DBX?
Excuse me, what happened?
Your own key in the DBX database? What happens?
DB and DBX database are like top at the bottom, so there are no other databases below them, basically. So you always have to sign updates to the DB and DBX with the KEG key. But in the reality, as you can see in that script, I left it there for the demonstration purposes. I am signing all the keys with the PK with the platform key. So you should sign the DB key with the KEG key and KEG key with the PK key, but you can, and it is even allowed by the specification. You can sign everything with the PK key. It is.
So idea is that vendors will certify the keys for OS vendors and so on. So that was the idea originally. That I don't know, Dell or whoever will sign the keys for the Red Hat or someone.
Well, I don't know pretty much what was the story behind this idea, but if you don't have your own keys, like imagine that you bought a brand new machine and PK key, for example, it's Lenovo. So in Lenovo case, PK key is owned by Lenovo, and then in a KEC database, the one below, you have Lenovo key and Microsoft key. And in DB you have Microsoft key. And then if you want to run some binary, you either disable SecureBoot or you have to run something which is signed by Microsoft or Lenovo, basically. Yeah. And Microsoft provides you with the... They provide certification service. Sorry, not certification, signing. They provide signing service. And for example, if you want to have your binary signed by Microsoft, you would have to deliver the binary and source code to them. They will do some security checks on their source code, and after a couple of weeks, and once you pay them, I guess $200, I'm not sure, they will sign your binary, and then you can run it on your own machine. So yeah, so basically keys are enrolled in a firmware, and then whoever owns the keys have to provide a way how to sign binaries with those keys, basically. And by default, Microsoft has keys installed in every laptop, and then Microsoft can sign binaries it wants, and those can be run on such laptop. I mean, in Fedora, default Fedora setup is a bit different from what I showed here, and it uses sort of a hack to the spec. I mean, they use extra database which they call MOK, machine owner keys. This is like a separate database implemented by the tool. In default Fedora, there is a tool called shim, and that shim tool is basically it has been signed by Microsoft, and then firmware will launch the shim tool, and then that shim tool knows how to basically find the grep binary and link the grep, and then it will jump to the grep code, then grep, you will see the grep then, and before it jumps to the grep, it will verify that grep is signed with the Fedora key, and the public part of embedded in a shim binary. So it is like a weird setup. I mean, shim is signed by Microsoft, then inside shim there is a public part of a key which Fedora uses to sign grep and kernel. Then shim links the grep, jumps to that code, before that verifies that binary is properly signed. Then you will see grep menu, and before you see actually the menu, grep will find all the kernel binaries according to your configuration, and it will ask back shim, hey, please verify the signature on that kernel binary, because grep itself doesn't contain any crypto code, so it calls back to the shim to verify, please check the signature on this kernel binary. And that's, I mean, I don't think that's particularly good design, but I know that there are like use cases which they want to support. For example, dual booting Windows, which I don't care about personally, and maybe that's what I didn't mention yet. I mean, if you have your own keys and Fedora key, for example, like in a setup I showed you, you are basically, and SecureBoot is enabled, you can't boot Windows because firmware will refuse. Because Windows Bootloader and Windows kernel are not signed by your own keys or Fedora keys. So that is the one thing I should emphasize, that using the setup I showed you, you will not be able to dual boot. So if you want to dual boot, please use default Fedora setup. But I mean, it is what it is. So, for example, that shim I am talking about, it bundles like crypto libraries, like OpenSSL for verification of the signatures. And then, like I told you, grub calls back to the shim, and shim does verification, returns back to the grub, and then grub can continue in a boot process, basically. So you have firmware itself contains crypto code because it has to do verification of signatures, and then shim contains crypto code. So you have two layers where things can go wrong. So if you don't care about Windows and you don't care about other operating systems, only care about Linux, then you can use the setup I showed you, and you can get rid of the shim layer.
How do you update UEFI?
Sorry?
Well, we have BIOS updates
Yep.
on the older machines. UEFI is just a new kind of BIOS. You want to update it, and the vendor discovered that they have bugs there. So they check it with the APK key, right?
Yeah.
So you shouldn't delete it if you want to ever update your UEFI firmware.
That's actually a good question. I think that's the case. Yes, you would have to disable SecureBoot. In a setup utility, you usually have a flag, enable, disable. So for a firmware update, you would have to disable it because usually firmware updates are done via some application which vendor delivers to you. Yeah, you will know about that.
Well, if it's signed with their APK key, you don't need to disable SecureBoot.
The vendor normally signs the EFI binary that does the update.
Yeah, so that's what and you can't run such binary if you have only your own keys.
Correct.
So you would have to disable SecureBoot for that time period, run the binary which was given to you by a firmware vendor, update the firmware, and then enable SecureBoot back. So
Unless you signed the firmware update yourself.
yeah, maybe you can do that. I didn't try it, so I'm.
Kind of hardcore.
So question in the back.
I actually have two questions.
Yeah.
One of them is you mentioned that the shim contains OpenSSL, right? So in case there's a new OpenSSL which fixes some serious security bug, do you actually have to recompile shim and get it re-signed by Microsoft, or how do you deal with this?
That is my understanding. That if you do some changes to the shim code, you will have to deliver that new code to the Microsoft certification service to sign by Microsoft.
Which takes about 2 weeks. So
Yes, that takes time.
Your
Yes.
systems are actually vulnerable. Possible that.
Well, it's a very small amount of code, so that's what you want is something very small that's not going to have a lot of issues.
Yes, that's the case.
And another question, you said that group is calling into the shim to get
Yes.
verification services.
Yes,
Can
shim.
it just call directly into the UEFI?
Shim establishes shim implements its own UEFI protocol, which is then used by grub, because UEFI API doesn't have like top level API, please verify signature.
Okay.
It has API, basically what systemd boot is using is UEFI API called load image. And in a process of loading that image, the signatures are verified in case SecureBoot is enabled, but there is no API to actually just verify a signature. So shim itself implements it extends UEFI firmware. It's a good example how you can actually extend the API which firmware provides you. Just look at the shim code and you will see how they do that, how they extend and provide their own API for grub to call back.
Thank you.
Yeah.
So what happens if I verify a signature of the image, then change the image, and then load it?
So you do what? You verify the signature?
Yeah, mod probe. Mod probe reads in the module in the then make a system call, load the image.
Mhm.
So the loading is checking the signature and then loads the. So what if this
So
memory
you are
is also
suggesting that this scheme is vulnerable to time of check, time of use bugs in a mod probe,
Yes.
and you are probably right. I mean, yeah, I guess I never checked the mod probe code, but
Well, you use module signing to get around that.
But what you are suggesting is that I check the signature and then I load the module, and in that very short time window between I do check and then load, somebody would somehow, but he would have to
Well, you would load
hack your kernel anyway, because how they
Go to kernel mod probe. I have a mod probe by fork another thread, which is just touching.
yes,
the
but if you
just need to read the module into memory first and then validate the signature, because you
Yes.
have to validate the contents of the module
yeah
to validate
you would
the
have to
signature.
have
So the module is loaded first,
Yes.
Yeah.
then the module is validated,
Yes.
and the code that is already validated is then inserted into the kernel.
yes.
At this moment, you can change it.
No, you can't.
No.
Why?
Because
you need to write it that way.
because attacker would have to break like the memory management subsystem of the Linux kernel, right, to hack into the mod probe. Like he would have to attack or somehow get into the mod probe process to change the memory mod probe already.
No, you said that
So
this,
mod
this,
probe
this
is
thing is not protecting you against user space attacks. So we are not tracking mod probe code. Mod probe code is malicious. We assume this.
That's fine, because mod probe code just pumps some sort of binary into the kernel space, and then the binary which is pumped into the kernel space is basically off limits to the user. It cannot be changed. When it's in the kernel space, you verify the cryptographic signature, and then you insert it. But there's no way the user can actually change the module piece.
Okay, so it's copied to kernel and then verified. Okay, makes sense.
okay. So, some more questions, Marcel?
So for clarification, so in your setup, not using shim, you write your key directly to the PK database, or?
Yes, you.
So you rewrite the original key.
Yes,
like-
Lenovo key is not anymore there.
So how would
And-
Lenovo key back on?
You would have to download Lenovo key or back up the Lenovo key before you delete it. So you would have to read the contents of that EFI variable, basically, what actually it is right now, put it somewhere.
Is it possible to have just one platform key?
Yes, it is possible to have just one platform key.
So it's not really a database, it's a place for one key.
Platform key is for one key, and then all the others are, you can have multiple keys.
Okay,
So,
you
I'm
write
going to-
you write the platform key, and then you have keg, right?
Yes, and in KEK database you can have multiple keys.
So when you write your own key there, if you edit and the Microsoft key still is there, or
It can be there if you want to.
but you can remove it.
You can remove it, yes.
Okay.
So it can be there if you want to, and even in a DB database you can leave the Microsoft keys,
So
and then you would be able to dual boot.
yeah, okay,
just
that's
what I
I'm
should-
going to ask. Okay. Yeah.
Yes. So
and you don't need to use shim then.
no. But the setup I showed you, which you have only your own keys
Yeah. Okay.
and Fedora key, you are not able to dual boot because you are not able to start Windows bootloader.
But then why using shim when you can have those two keys there and do it?
I mean, that's the question for people who implemented that scheme in Fedora. I mean, they wanted to use grub. That's the one thing, I guess. Grub is the default bootloader in Fedora, and it would be very hard to get rid of that. And I don't know. So I guess maybe the story starts there. That their requirement was to use grub.
Yeah, okay, that makes sense.
Question?
Yes, stupid question. Can I sign a Windows bootloader with my key?
You can sign whatever you want. So basically,
Even with your setup, I'm able to boot Windows if I sign. They
yes, if you take that binary, there is a specification where those keys are placed in a binary. So you just find it, take it out, and put something else there. You compute the hash, sign it, and put it to the binary again.
That would change the hash.
No. As far as I understand, hash is computed in a way that
It's the inside of the signing envelope. not
yes,
the outside.
key is not part of that computation. So you basically compute the hash, you sign it, and then you put it signed hash into that binary. So I can resign my kernel basically. It's by default signed by Fedora key, so I throw it away, sign it with my own key, and I can boot it then. Okay, so yeah, so basically we sign the keys, sign the signature lists, and then we enroll them into the firmware. And then once we enroll here at the bottom, PK, platform key, that automatically takes the platform to the user mode. It should. It actually doesn't. You have to reboot. And that's probably a bug in the firmware. Because, or maybe it does, but it doesn't tell you. Maybe bug in kernel, I don't know. I would have to check. Because if I run bootctl, it tells me that SecureBoot is disabled and platform is in setup mode, I guess. But it really should say that SecureBoot is actually enabled and the platform is in user mode once we get to here. Okay, so we already talked about alternatives, how you can implement SecureBoot. So actually, you don't have to use any bootloader. You can just sign your kernel and use EFI firmware to load the kernel directly. There is a EFI variable called boot order, and whatever is defined in that variable will be at least tried by the firmware. And if you define a path to your kernel, which will be on a EFI system partition, then you can boot basically without the bootloader. Then there is a grub plus shim approach we discussed, and there is one more thing which is related to grub plus shim approach, and that is the tools made by James Bottomley, the SCSI maintainer in kernel. He also does SecureBoot things and EFI stuff. So he sort of did a hack where they have separate key database called MOK. They install key there, and then they do very weird thing, which is sort of, it is, as far as I know, it is not standardized, and it is like a hack, but it works. And the point is that they override something called EFI security architecture protocol, and they install their own hook into that. So basically, they chain another key database into that chain. So basically, if the key is not in PK, not in KEK, not in DB, it will try MOK as well. So they have like, I don't know, it's a couple lines of assembly, but it is a hack, and so far, as far as I know, it is not standardized. It is not allowed by standard to do such hacks, but they tried it and it worked. They claim that everyone is using basically the Intel implementation of UEFI. Only ASUS is doing their own thing, and they also tried hardware with the ASUS firmware, and it worked everywhere. So they do that. I mean, they invented their own database and installed that override into that protocol. So that database is also checked. I don't know. up to you to decide what you think about it. So now UEFI development. So very quickly, the main thing you need is, if you want to experiment with all the stuff we talked about, so you should get EDK2 installed on your machine. So EDK stands for Efi Development Kit. Here is the repo. You just add that repo, or if you are on Fedora, CentOS, or RHEL. If you are on Ubuntu, I guess you just have to unpack RPM and copy the files to the correct destinations. So that is the repo, and from that repo you can install that package. That package actually contains binaries for UEFI firmware, for open source implementation of the UEFI firmware, which actually lives on GitHub. And the guy, Craxel, he actually runs Jenkins instance against that Git, so you can have basically firmware built every day. So you can experiment with the fresh master. May not work from time to time. It depends. So couple other things. If you are using UEFI, you should have your disk formatted in a way that it uses GPT partition table. I mean, there is no reason not to use GPT. MBR is terrible. You can have 3 or 4 partition at most, and they are small. So you should use GPT. I mean, all the standard tools provides that functionality. So FDisk, CFDisk, whatever you are using, all provides possibility to use GPT instead of DOS partition table. Then you basically create one partition, which will be your boot partition, and you format it as FAT32. That is mandated by the firmware specification, and you mount it somewhere. I recommend, and what in the image is done, is you don't specify anything in FSTab, and you let systemd do its magic. It will discover that you are using GPT partition table. It will figure out which partition is supposed to be your boot partition, and it will mount it automatically. So you don't do anything, systemd will do it for you. Then you can use Bootloader. I showed you, so I really recommend using systemd boot. It's very lightweight bootloader, 2,000 lines of C code basically to implement basic functionality of well, I don't know, who uses grep for anything else than just booting their laptop? Okay, one guy, so then systemd boot is probably not for you. But for everybody else on the laptop setup, I don't see a way why should I bother with grep.
Can you document that process? Because I actually tried to switch fairly recently, and I was able to succeed, but I know quite a bit about this technology. I don't think anyone that is not would be able to switch to it.
Yeah, that's
from Grub, and it's not even packaged in Fedora. So.
Okay, I mean you mean systemd boot?
Yeah.
It is part of systemd RPM.
It's not built.
It is.
I checked the binary.
User lib systemd boot EFI path. I mean, I can.
Well, this was a while ago, so maybe it was.
So
maybe
okay, so
I might have had an old package, but
yeah, maybe. So try Fedora 23 rawhide. It should be there.
Okay.
If not, file a bug. It should be there. So once you have that, once you have systemd boot, which everybody should have because it's packaged in systemd, you should have top-level tool bootctl, and with that you can do nice things like status, install the bootloader, and you can install, also for the development purposes, I recommend installing EFI shell. But these days, the firmware itself embeds shelf in itself. So basically, you don't need to have separate shell binary. It is in a firmware by default, and you can run it from the setup utility menu. It is like boot device menu, and in there is a sub menu where you pick EFI shell. In an image I provided you, there is a separate shell binary installed, so you can play with that. So the actual firmware implementation itself is at that GitHub account, Tiano Core /EDK2. Tiano is an old name Intel used for that stuff. I mean, legacy. These days it's like, it should be named like Intel /EDK2, but doesn't matter. And to actually do some EFI development, you need really basic tools. You need just GCC, make, and binutils, and that's pretty much it. You don't need anything else. And GNU EFI devel package. So here's really simple Hello World application where I would like to show you a couple of differences between the normal C Hello World and Hello World for EFI. So as you can see, the main function is called a bit differently. It's called EFI_main convention. EFI, it takes a couple of parameters, so it's two of them. EFI handle to image, so basically it is a data structure basically describing the application itself when it is running. And then system table. In the table, there are a couple of function pointers to basic protocols like output. As you can see here, console output. It is from that systup structure. So that is the pointer to the protocol. We can see that then the protocol is used here. So, and we will be calling a method of that protocol output string with two arguments. This pointer basically, and the actual string we want to print. Yeah, you can see here that I'm using L prefix because all the strings in UEFI applications are basically UTF-16. That's unfortunate, but it is what it is. I mean, the standard itself was designed in 90s, and I guess back then UTF-8 was not that popular. So they went what they had. Okay, so development environment, like I said, very simple. GNU make binutils. Yeah, so you see here that I am calling basically this function, but I am not calling that function directly, even though I have pointer to that EFI function. I'm calling that function via the UEFI call wrapper because UEFI uses different calling convention as GCC by default, and that wrapper will provide you with the correct calling convention for the current target. So basically, it doesn't matter whether you are compiling for 32 or 64-bit code. If you use this wrapper, it will do just the right thing, depending on the target. So yeah, I mentioned UCS2 strings, so that's basically UTF-16 with minor differences. For the most part, it's a UTF-16. Yeah, and there's no standard library, basically. You can't use memcopy. There are routines in GNU EFI package. There are libraries you can use. You have to look in the header file to see what's there. API it resembles Windows APIs, like the conventions for the code. It is camel case and stuff like that. So I mean, it's not that nice, I would say, as standard C APIs we deal with every day, but whatever. It is what it is. And yeah, so for a more complex example, you can actually look at the code of Bootloader we used in our demos. I really recommend looking at that code because it uses different protocols like output, graphics, and stuff like that. So, and it is very short. It is maybe 2,000 line of code, C code. So you can get the feeling how would you go about implementing non-trivial EFI application, and it's not that hard. Yeah, and I'm out of time, and that's pretty much it. So thank you for your time. And I was told to hand scarves for questions, so I guess Richard will get one. Oh, you got one. Okay, so. Oh, so we have 2 spare tickets to the party. Who doesn't have ticket to the party and wants to go there?